Computed tomography or CT is an excellent tool for modern medical imaging. With an excellent image quality for patient diagnosis purposes. CT imaging is carried out very fast. However, CT uses X-rays, which are ionizing radiation, so its use can cause harm to the human body. In addition, the CT system is very complex, so there are the potential errors from each stage that can produce images leading to misdiagnosis. To minimize this, CT must always be monitored so that it's always performing to standard. This monitoring is done by a complex procedure known as quality control or QC. The QC procedure consists of daily, monthly, and annual tasks. Each procedure is time-consuming. Manual QC can take many hours. Manual measurement of image quality parameters can also lead to a bias due to the subjectivity of examiners. IndoQCT presents to answer the needs of QC, which is automatic, fast, objective, and accurate. IndoQCT originated from comprehensive research published in reputable international journals. Unlike some existing software that can only be used on one type of phantom and with limited parameters, IndoQCT can be employed to measure numerous parameters of image quality from various phantoms in the market. IndoQCT can also measure some image quality metrics directly from the patient's clinical image for easier and more objective dose optimization. IndoQCT can be utilized by various groups: clinical medical physicists, researchers, lecturers, students, or for those who want to learn about CT. It provides convenience, efficiency, measurement objectivity, universality, and portability. IndoQCT can be downloaded from the website www.IndoQCT.com. Computed tomography or CT is an excellent tool for modern medical imaging. It's available in almost all hospitals throughout the world. CT produces 3D images with an excellent image quality for patient diagnosis purposes. CT imaging is carried out very fast. However, CT uses X-rays, which are ionizing radiation, so its use can cause harm to the human body. In addition, the CT system is very complex, so there are the potential errors from each stage that can produce images leading to misdiagnosis. To minimize this, CT must always be monitored so that it's always performing to standard. This monitoring is done by a complex procedure known as quality control or QC. The QC procedure consists of daily, monthly, and annual tasks. Each procedure is time-consuming. Manual QC can take many hours. Manual measurement of image quality parameters can also lead to a bias due to the subjectivity of examiners. IndoQCT presents to answer the needs of QC, which is automatic, fast, objective, and accurate. IndoQCT originated from comprehensive research published in reputable international journals. Unlike some existing software that can only be used on one type of phantom and with limited parameters, IndoQCT can be employed to measure numerous parameters of image quality from various phantoms in the market. IndoQCT can also measure some image quality metrics directly from the patient's clinical image for easier and more objective dose optimization. IndoQCT can be utilized by various groups: clinical medical physicists, researchers, lecturers, students, or for those who want to learn about CT. It provides convenience, efficiency, measurement objectivity, universality, and portability. IndoQCT can be downloaded from the website www.indocct.com. Computed tomography or CT is an excellent tool for modern medical imaging. It's available in almost all hospitals throughout the world. CT produces 3D images with an excellent image quality for patient diagnosis purposes. CT imaging is carried out very fast. However, CT uses X-rays, which are ionizing.
Okay, good afternoon all participants. Assalamualaikum warahmatullahi wabarakatuh. We continue our summer course today with the online summer course in Medical Physics 2025 in the QCT for CT image quality measurement. In previous lectures, we have discussed many things about the CT parameters using the phantom. Now we have a special topic, the advanced image quality measurement from patient image and its measurement using IndoQCT. And in this topic, we will try and learn how to measure image quality directly from patient CT image. So this topic will be delivered by Dr. Hairul Anam. And before we start our lecture, I want to remind all of you to fill the attendance links. So, Dr. Hairul Anam, are you ready?
Inshallah.
Okay. Dr. Anam, the time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Can you see my screen?
Yeah.
Okay. Now we will. Yeah. Sorry. Yeah. Now we will discuss regarding advanced image quality from patient image and its measurement using IndoQCT. This material should be delivered tomorrow, but because Professor Wahyu today cannot deliver the material, so I move forward to deliver this material today, and Prof Wahyu will deliver material tomorrow. Okay, we will discuss regarding the image quality directly from the patient images. Okay, this is the table of content of this material: introduction, noise measurement, MTF measurement, LCT measurement, and centering measurement directly from the patient images. Okay, this is the introduction for the dose optimization. It is important to achieve using this principle as low as reasonable, achievable LRA. It means that we should have the good image for diagnose the patient, and this image should be obtained with smallest possible dose. For the dose optimization, the first thing is image quality, not the dose. It means the image quality should be kept with the acceptable quality. And to achieve this image, we should use the smallest possible dose. This is the dose optimization. So in the dose optimization, the image quality is very important. Okay, until now, the dose and image quality is usually measured using phantom. For example, for image quality, we use the IBM phantom, SCR phantom, CAT phantom. And for measuring the dose, we use, for example, CDI phantom and so on. It is very good for controllable variable, such as the MA, the impact of filter, the impact of KV, the impact of slice thickness, the impact of image reconstruction, and so on. But these parameters, it is can be measured for the uncontrollable variable. Yeah, so we have the control variable and uncontrolled variable. The control variable such as tube current, tube voltage, rotation time, pitch, slice thickness, field of view, and so on. And uncontrolled variable such as the patient size, attenuation, scan part of the body, and so on. And as we already discussed before, that the image quality is strongly depend on the size of the patient. For example, if we scan patient with the same protocol, with the same tube current, with the same kilovoltage, if the patient is bigger, the noise will be higher compared to the smaller patient. So the image quality is not only depending on the control variable, but also depends on the uncontrolled variable. So it is important to measure the image quality directly to the patient. So now so many effort from the researchers around worldwide to measure the image quality directly from the patient. For the dose adapting with the size of the patient is SSDE, size specific dose estimate, and we didn't discuss SSDE in this summer course. We had already discussed in the last summer course in the 2024, and now we only focus on the image quality. So, as I already mentioned, the image quality, the ideal approach is to optimize and monitor CT protocol is to directly on the clinical image of the patient. This is the image, the figure from the book of Professor Ihsan Samei. This is the experiment. We have the control experiment and critical and clinical reality. So for the control experiment, we can adjust the MAS, KV, CDA fall, rotation time, and it is important to measure these parameters. If we move forward, we use the simple phantom, just like RCR, CAT fan, IPM. This is the simple phantom. And we can measure many parameters such as the MTF, NPS, contrast, detectability index. And if we move forward, we should measure the image quality from the anthropomorphic phantom. And we move forward again, we can use the virtual clinical trial. And if we move again, we can use the hybrid data set. And last, we can use the clinical trial from the clinical practice. It is the reality of the patient. But measuring the image quality from the patient still many challenging, still many problem. So even though now many researchers try to overcome the problem one by one, and in the today's talk I will deliver how to measure image quality directly from the patient, although still many challenges. Okay, we will measure at least 4 parameters: noise, MTF, LCD, and centering from the patient images. Okay, and now we move to the first parameters. It is noise from the clinical CT images. As I already mentioned, that fluctuation, the noise is the fluctuation due to the uh, uh, in the pixel of the image due to a problem when we scan the phantom or in the image reconstruction or in the data acquisition. So the fluctuation due to anatomical variation are not considered as noise. So it is difficult to measure the noise directly from the patient because so many parts in the image of the patient. So we can suppose that within patient images, it is not likely exists the homogeneous part within the patient. So it is very difficult to measure the image quality directly from the patient, especially for measuring the noise. And some expert think that the noise from the patient can be measured directly using subtraction method, meaning that the patient scan twice, and then we have the 2 images, and then we subtract one image with another image. So the anatomical variation can be removed, and the remain is only the noise. It is the idea, the first idea to obtain the noise from the clinical image. This is the example. But by using this method, we should scan the patient twice. And of course, it is not good idea because we give the dose twice to the patient. This is an idea. And after that, we can measure the standard deviation to obtain the noise. And of course, the standard deviation in this position is twice of the noise. So we can divide our result by 2 to obtain the noise value. And this is the first paper tried to measure noise from the patient images. This paper is written by Professor Christiansen, published in the AJR, American Journal of Ransonology. The title is The Automated Technique to Measure the noise in clinical CT images. The idea is like this. In the left image is the original image of the patient. And then we will measure the noise in this image automatically. So the idea, we can measure the image from the aerated tissue, or fat tissue, or soft tissue, or bone. In this example, in this paper, the authors use the soft tissue. So they have the limit of pixel value from 0 to 100 Hounsfield unit. So if the pixel value more than 0 and less than 100 Hounsfield unit, so this pixel will be included in the calculation. And then we use the kernel with specific size, for example, 9 by 9 or 7 by 7. And then we calculate the SD in one location from kernel with size 9 by 9. We calculate the SD. After that, we move one pixel to the next pixel, and then we calculate again the SD, and then we move again, and then we move again until we have measured, we have calculated the SD from all pixel. From this process, we will have this one, SD map like this. And after getting this SD map, and then we develop the histogram. And the x-axis is the SD, and the y-axis is the frequency. This is histogram of SD map. And we can suppose that the noise is the SD value when the frequency is maximum. So in this example, this is the frequency. So if we draw the line to the bottom, to the x-axis, so the x-axis is the noise, and this noise called as the GNI, Global Noise Index. This is the idea proposed in this paper, and this is the how to create SD map by using kernel. In this example, we use 3 by 3, and we calculate SD in one location, and then we move to another pixel and so on until all pixels are calculated. By using this equation, this very simple equation for calculating the SD, standard deviation. And in this trial, the author make variation in the kernel from very only 3 by 3 up to 30 by 30. And we can see here, if the pixel less than 20 by 20, so we will have the noise flat one, stable one. But if the pixel, if the kernel more than 20 by 20, so there is increase in the global noise index, meaning that in this position, if kernel very high, so the fluctuation in the anatomical variation is included in the calculation. But if the kernel less than 20, we can get the stable global noise index. So it is a very good achievement. So by this fact, we can set the kernel size around from around 9 by 9 to maybe 19 by 19. It is stable. Maybe we can choose maybe in the middle, for example, 13 by 13. It is good option to set the kernel size for measuring global noise index. This is the result in the paper, and this is the comparison of the automatic noise measurement compared to the manual measurement. And we can see here there are comparable results between the automatic one and the manual one for the different kernel reconstruction kernel, different dose level, and different slice thickness. Yes. It is very convinced that the automatic method is good enough to obtain the accurate noise level. And this is another result. The y-axis is the global noise level, and the x-axis is the observer noise measurement. And we can see here there is linear correlation between the automatic one and the manual one. So it is very convinced us that the automatic automatic method is very good result. And there are many other techniques. This technique is proposed by Professor Marcus, and this method is published in the Medical Physics. The title is a method to extract image noise level from patient images in the CT scan. The idea is like this. We can suppose that outside of the patient body is air, and we know that air is homogeneous. So because the air is homogeneous, so the noise within air depends on the input parameters. So we can imagine after that we can measure the noise on the air outside the patient. This is the idea. And then the Professor Marcus compare the noise within the patient image and outside the patient images. And you can see here, for example, this one from A, B, C, D, we have images from different MA level, different tube current level, scan with different tube current. And we understand that if tube current increase, so the noise increase. And we can see here that the noise inside and outside the patient increase with the increasing of tube current. So it is a strong correlation with the noise within the patient and outside the patient. And if we have the dependency, the image within patient can be estimated from the noise outside the patient. This is the idea for measuring the noise automatically from patient images. So in this algorithm, it is the phantom, and then this phantom is segmented, and then we can calculate the SD map, and from the SD map we can obtain the histogram of standard deviation map, and we already discussed this. And the idea of the Professor Marcus, this is the image of the phantom or patient, and then we segment, but we segment not area within the image, but we segment the area outside the phantom. So like this. This one is the inside patient is segmented, and this one outside the patient is segmented. And then we calculate the noise map outside the patient or within the air. And after that, we develop the standard deviation map, and then we develop the histogram of the SD map. And then we can also calculate the GNI. This one is GNI within the patient, and this one is GNI outside the patient. And of course, we can make the relationship, and this is the result. There is strong relationship between the GNI within the patient and outside the patient. So based on this fact, of course, we can estimate the noise within the patient using the air area outside the patient. And by using this method, it is advantageous. Yeah. For example, if we measure the GNI within the patient, for example, in the thorax area or in the skull area, there are so many bone here. So maybe we cannot find the homogeneous region to calculate the GNI. But if we measure the noise from outside using air outside the patient, so we can easily find the homogeneous region, and we can calculate the SD map, and after that we can develop the standard deviation histogram, and after that we can obtain the GNI. This is the idea, like this. This is the relationship, the R square values between the GNI inside and outside the patient. This is another result. So this method is also very interesting for measuring the noise from the clinical patient images. And this is my paper. This is the another approach to measure the noise automatically from the patient images. In the method introduced by Professor Christiansen using the part within the patient images, and from Professor Marcus using the part without outside the patient images. And in this idea, we're not using segmentation. So we have the image, and after that we just calculate the SD map from all images without segmentation. And after that, we do not make the SD histogram, but we decide the minimum value. Why the minimum value? Because we already understood that the noise is the fluctuation within homogeneous part. And if we find the homogeneous one, the SD should be minimum. So in this idea, we propose to detect the noise with we have the SD map, and then we detect the minimum value within the image. This is the idea. And this is the result. Our result, the x-axis is tube current, and the y-axis is the noise. Okay, and we can expect that if the tube current increase, so the noise will decrease. This is the result is as expected. And this is the noise with the different level of the iterative reconstruction. So if we use the strong level of the IR, so the noise will decrease. So this result is as expected. And we also compare our method with the previous one proposed by Professor Christiansen, and the result is very good. And this one is the result, and by using this method, we can measure the noise not only in the abdomen area, which is the homogeneous region is very much available, but we can also measure the noise from the neck, from the skull, which is the homogeneous region is only very little. So this is the result. We can measure the noise from the anthropomorphic phantom, and then we scan the anthropomorphic phantom, and then we scan with the different tube current. We have 3 different tube current, and then we have images from top of the head to the this position, and then we can measure by using our approach. This is the result. So we scan with the constant noise, constant tube current. We can see here in the abdomen position, this one in the thorax position, this one is the neck position, and this one in the head position. So we have obtained the very accurate noise level like this. And if we calculate the average, and we can show in the box plot diagram, we can see the result. This is the noise level with the different tube current. And if we overlay the noise level with the diameter of the patient, we can see here the result is very good. Yeah. This one is the 3 method for measuring the noise level automatically from the patient images, by using the GNI from inside the patient, using GNI from outside the patient, and we can also measure the noise from the minimum value from the SD map. Okay. And this is another paper written by our team, published in the Biomedical Physics and Engineering Express. And this paper, we developed the computational phantom for validation of the automated noise measurement. Yeah, because if we use the computational phantom, the noise can be added, and the noise can be controlled by ourselves. This is the design, and this design is already available in the IndoQCT. We have the material from very low pixel values to the very high pixel values, and then we have the line here, so that there are no homogeneous region outside the region of interest. The region of interest is only limited in this area. Okay. And then we add the noise level with the different level. And this one, we can add the noise by the synthetic noise level, and then we also make the noise, add the noise from clinical real images. So we have scan of the homogeneous phantom, and then we combine our computational phantom with the real images. So we have the design like the computational one, but the noise is real from the real CT images. And then we measure using our method, and this one is the phantom, and this one is the SD map. SD map, and then we can calculate the minimum values of the SD map, and this values is considered as the noise. Okay. This is another parameters. We can see that the result is expected. This is our result with the kernel size, and this one is the measured noise, And then we can compare the ground truth noise. We have the ground truth because we use the computational phantom. We know the noise and we add the noise with our setting. And this one is the measured noise. We can see here there is strong correlation between the ground truth noise and measured noise. And then we have the factor uh, that is used to convert from the ground truth to the measured noise, or from the measured noise to the ground truth, like this. This is our correlation, and by using these values we can convert from the measured noise to the estimated noise with the ground truth. This is the example. This is the noise from the different kernel size. We can see here, if the kernel size is very high, so the noise is also increased rapidly because of the non-homogeneity. And after we correcting with the formula previously, and then we can see the result like this. So by using this method, we can obtain the relatively accurate noise from the patient images, and in this case by using the computational phantom. And this is paper written by our team, and we we compare our dose and noise level for dose optimization. This is the we have the many images from the pelvis, abdomen, thorax, and head, and then we calculate the DW. The DW is the water equivalent diameter of the patient, and we also calculate the dose SSDE, size specific dose estimate. This is the dose take into account the size of the patient, and then we calculate the noise from our approach, and this is our result. This one is for measuring the SSDE, and this one is for measuring the noise. This is our result. Our result in the red one is the noise, and the SSDE, and the blue one is the noise. We can see here for the body, for the thorax, and for the pelvis, the image is scanned with the tube current modulation, but for the head, we use the constant tube current. And we can see here the dose is stable, but we can see here the noise is decreased with the increasing size of the patient. The SSDE decrease with increasing size of the patient, and the noise is constant. Yeah, it is a very nice result, and we can see here the result. This one is the dose from the pelvis, abdomen, and thorax, and this one is dose for the head, and this one is the noise. We can see here that the noise in the head area is lower compared to the another location, and we can see here that the dose is very high in the head. So by using by seeing this fact, so we can optimize the dose to the head. So we can decrease the dose. Of course, if we decrease the dose, the noise will increase. It's no problem because the noise in the head is still very low. So actually, by using this fact, we can optimize. We can optimize our protocol in the hospital, especially for the head scan. Okay, of course, we can measure the noise using the IndoQCT. And the IndoQCT having three options. We can measure the GNI inside the patient, GNI outside the patient, and also noise from the minimum values of the estimate. This is the example. If we measure the GNI inside the patient, This is the SD map, and this one is the histogram of the SD. This one is the GNI outside the method, or GNI outside the patient. You can see here, this is the patient, and this one is for measuring the SD map, and this one is the histogram of the SD map, and this one is the minimum SD map method. Okay, and this one is the smallest position, and this one is considered as the noise. Okay, that is the noise measurement directly measured from the patient images. And now we move to measure the MTF. MTF from the patient images. This is the paper written by Professor Iksan Samay group. And this one is the image. This one is the segmented image, and then they reconstructed to the dimensional images, and then they make the profile across the skin of the patient, and then they have the ESF at ASF at spread function, and then by the differentiation they have the line spread function, and by Fourier transformation they will have the MTF by using this method. This one maybe it is the problem because our body is not homogeneous, but in the outside our body is homogeneous because of the air. So in this paper they propose the specific method. The name is the tail replacement. So we have the ESF, and then we take the ESF from the outside the patient, and then we rotate and we locate in the another tail. So by using this method we will have the very good ESF. This method is called as the tail replacement, and this is the result. This is the result of the MTF measurement directly measured from the patient. It is also a very nice idea to measure the MTF. This is another method, and actually this paper is recently published in the GSCMP, Journal of Applied Clinical Medical Physics, by the Zheng Liu from China, and they also use the IndoQCT for measure the MTF directly from the patient. They also develop their own software and compare with the IndoQCT. Basically, they use this one. We can see this is the phantom, and this one is the phantom, the patient, and then we detect the edge of the patient, and then we draw the line, and we have the ESF. After that, we get the LSF, and by using the Fourier transformation, we have the MTF. Okay, this is the result. The MTF directly measured from the patient images, reconstructed with different kernel. This is the result. This is also the trial and effort how to measure the MTF directly from the patient images. This is the IndoQCT software. We can measure the MTF directly from the patient images. But it is important to note we should choose the location so that the part of the image is homogeneous one. Okay. Okay, and now we move to the third parameter for measuring the LCD, or low contrast detectability, from the patient images. Okay, yesterday we had already discussed about the SDLCD, statistically defined low contrast detectability. Okay, by using the homogeneous region, and then we make the ROI, many ROI, and then we calculate the average, and after that we make the histogram, and then we have the distribution like this. And if we suppose that the signal and background having similar diagram, so the object can be differentiated from the background if there is certain distance between the two Gaussian function. Okay, by using this formula, it is measured on the homogeneous region. Okay, within the patient, within the phantom images. Okay. And if we make the ROI with different size, of course, we can develop the CD curve. Okay. Yesterday, we have already discussed about the CD curve. And the idea, there is one question. Can we measure the LCD directly from the patient? Until now, the LCD or CD curve is still measured from the phantom in the homogeneous region. Okay, so I have an idea to measure the LCD directly from the patient, and this idea have been published in the Biomedical Physics and Engineering Express. You can download this paper. The idea is similar to the idea of the Malthus idea. Similar. Yeah. We have the patient. This one is phantom. Phantom. Until now, we measure the LCD inside the phantom. Okay, and we can develop the CD curve. Okay. And we use the idea from the Professor Malthus. So we segment the area outside the phantom or outside the patient. So I already mentioned outside the patient is air, and of course the air is homogeneous. So in this homogeneous region, we can make the many ROI. Okay, and after that we can develop the SDLCD like that. Okay, so it is similar to the idea of the Malthus, but Malthus only for measuring the noise, and this idea for measuring the LCD. But the idea is similar. Okay. So this is we can also measure that in the IndoQCT. And IndoQCT will make the ROI outside the patient or outside the phantom. And we can set the confidence level, and we will get the graph like this with the two Gaussian function separated with the certain distance regarding to the confidence level. Okay, and the last we will discuss about how to measure the centering from the patient images. The centering, it is important, and Professor Wahyu will explain this in the next day, tomorrow. And now we will try to discuss how to measure the patient centering using the clinical CT images. And this idea is already studied, and we published in the Polish Journal of Medical Physics. You can refer this paper. Okay, the idea is like this. This is the image of the patient, and then we segment the patient body, and then we calculate the the center of the patient using the centroid formula. Okay, this center of the patient should be in the center of rotation, but actually there is some degree of the differences, so it is the miscentering. Okay. Okay, and we measure the miscentering in the x-axis and the y-axis for the many images from the head, thorax, and abdomen scanning. And this is our result. We can see here this one is the miscentering in the x-axis, and this one is the miscentering in the y-axis. We can see here the miscentering in the x-axis is very little, but the miscentering in the y-axis, we can see the miscentering up to around 10 millimeters. Okay. So by using this fact, we can suggest to the radiographer to make adjustment, because their action because their setting is out of the center. Okay. Okay, by using the IndoQCT, we can measure. We can only choose in the one slice, and we can also measure the miscentering for all slices, and we can get the average of the miscentering. Okay, this is the example. The miscentering in the x-axis, in the y-axis. Okay, we can see here that the miscentering in the x-axis is only very little, but in the miscentering in the y-axis is already seen here. Okay, we come to the conclusion. The ideal approach to optimize and monitor CT protocol is to directly evaluate the level of image quality in clinical images, such as the noise level, spatial resolution, LCD centering, and now there are many effort to measure the image quality directly from the patient images. And by using the IndoQCT, we can measure the noise, LCD, also miscentering from the clinical images. Okay, this is all from me. And now we will try to measure the parameters using IndoQCT. Okay, please open your IndoQCT. And if you have any question, please write on in the chat box. Okay. Yes. Okay. Please open your IndoQCT. Okay, and now our IndoQCT is open. And now I will try to open the patient images. This one. This one. This one. So we can see here that the phantom is patient. And this one, phantom is patient. So in this image, we can measure many parameters. Now the first one, I will measure the image, measure the noise level. The noise level. Okay, and you can see here we have the method can be automatic and also can be manual one. And the algorithm, we have three options: GNI inside, outside, and also the minimum. In this example, I choose the inside. Okay, And then this is the kernel size we can set for the default is 11 pixel. And this one is for the limit for developing the SD map. And this example, the standard one is the minus 100 to 100 Hounsfield unit. Okay, this is the default. You can change these values, and you can measure the noise in the one slice or multi slice. Maybe in this example we use only one slice. Okay, if we agree with the parameters, we just click this button, calculate. This is our result. This is our result. This one is the estimate, and this one is the histogram of estimate. And you can see here the red line, and this red line indicating the GNI, Global Noise Index. Okay, and you can see the result here. So the noise is the 7.17 Hounsfield unit. Okay, this is using the GNI outside inside. You can also can choose the GNI outside. So you can choose this one, the GNI outside. Maybe the kernel is same, and then we calculate by clicking this button. You can see here. This one. So the estimate is outside the patient, and this one is the histogram of the estimate outside the patient body. And you can also calculate using the GNR, the minimum method. And in this one, we can measure the number of smallest. So if we set 10, meaning that we obtain 10 smallest SD, and we get them, and then we make average calculation. Okay. Of course, you can set this one with the different values. Yeah. Okay, and then I click this button. Yeah, in this method, there are no limit of the pixel values because we calculate the all pixel from all pixel. It is different from the inside or outside. So inside because we only calculate the SD only for the pixel within the range. Okay, this is the result. Okay, this one. And of course, you can also measure the noise from the multi-slice, but it takes a longer time. Okay. And now we move to the number 2 to calculate the MTF. In this example, we use the HMTF. HMTF, this is our method. Yeah, I think similar to the MTF measurement in the previous session. Okay, we have this one, and then if you agree, you just click this button, calculate. We calculate this one, and the software will detect the edge of the patient. This one, you can see. This one, we have many line perpendicular to the edge of the patient, and then from this line we obtain the ESF, edge spread function, and then we calculate the average of the ESF. This one is the average of the ESF, and then we calculate the differentiation. If we differentiate this graph, we will have this one, the PSF, point spread function or line spread function, and by Fourier transformation, we will have the MTF like this. And this is the method. Of course, there are still many uncertainty, yeah? So you can handle one by one in the next studies. Okay. This one is for measuring the MTF directly from the patient images. Okay. So maybe we can, for example, open the another image. I use the anthropomorphic phantom in this example. Maybe we will measure the MTF in this position. In this position, for example, in this location, for example. Okay, and then we calculate again. So the IndoQCT will make the ROI, the line, perpendicular to the edge of the patient. So it is not easy task to do. Okay. Okay, and we have ESF, PSF, and also MTF. Okay, and now we move to the to calculate the patient centering, and now I open again the patient images like this. Okay, for measuring the miscentering, we using this button, miscentering. Okay, we can choose the reference can be center of rotation and can be center of image. The center of rotation is from the DICOM info. Okay, and the IndoQCT will calculate the center of the image. So there are three center of the image, center of rotation, and center of patient. Now, the center of patient should be in the center of rotation. It is the good condition. But actually, in the clinical image, the center of patient not always in the center of the rotation. Okay, we can measure slice by slice. In this example, we can calculate this one, and we calculate this one, and this is the result. You can see here. This is the center of rotation. This point is from DICOM info. And this one is the center of the patient. As I already mentioned, the center of patient should be in the center of rotation. But in fact, in the clinical environment, the radiographer look at the patient so that the center of patient is not in the center of the patient. You can see here. Okay. This is in one slice. So we can also calculate for multi-slice. For example, in this example, we have the 38 slices. So we can calculate from the slice number 1 to slice number, for example, 38. So, and then we can calculate this one. This is the result. This one, it should be 0, but in fact in the y-axis, so there is tendency that the patient is lower than the center of rotation. Okay, I think maybe by using the IndoQCT, if you choose this one is patient, so we can also measure the CT number automatically. In this example, we choose this one, and then the CT number accuracy, and then we click this button segment. Click, and then we click in this location. So the software will detect the border of the organ, and then we calculate the average CT number. So it is, I think, convenient for do the study For example, to study the pixel values of the lung and so on. Okay. This is using the algorithm is the development of the, maybe you know, region growing method. This is the refinement of the region growing method for the segmentation. Okay. And you can also calculate the histogram, and then we segment, and then we look at in this position. So we will have, this is our ROI, and we also obtain the histogram of the pixel values within the ROI. Okay, like this. Okay, I think this from me. And if there any question, please discuss together.
Okay. Thank you so much, Dr. Anam, for the great presentation regarding the measurement image quality in the patient CT image. I think there are many asked questions and comments from the participants since it is an interesting topics. And we will enter the discussion session with the question from Miss Afra. Dr. Hoiro, did you mean in the real image patient, the standard deviation not represent the noise as in phantom image, only the high value of standard deviation it is? Or can you explain the difference between real patient image and the phantom in dealing with noise and standard deviation as two value related to each other? So, another comment. So, did you think that we will come to the stage that there is no need for phantoms and the patient image are enough?
Yeah. Measurement of noise from the phantom is for the quality control. Okay. And the measuring of noise directly from the patient is for the dose optimization. So we have the different purpose. Okay. And the noise measurement on the patient is, there is a challenge. So the researcher now try how to solve, how to make sure that the noise can be automatically measured from the patient images. So in this explanation, I have explained three methods to measure the noise directly from the patient images by using the GNI inside, GNI outside, and using the minimum estimate. Okay. By using this method, we can measure directly, automatically and directly from the patient images. And these values can be used for the dose optimization. Okay.
Is any comment from Miss Afra about the question? Yes, I think Miss Afra is enough with the question. Another question, doctor, from Mr. Mohammed Adavise. Can planar images be handled by IndoQCT? Which algorithm is the best?
Yeah. IndoQCT basically can be used for images other than city images. For example, we can measure the city, the image quality from the mammography images, from the DR images, or from MRI images. But for measuring the image quality, we should choose the manual one, the manual method, because for the automatic method, we rely on the city number, and city number is only for the city. So, can IndoQCT measure the MTF from the MR images? Of course, we can measure that, but using the manual method, meaning that the ROI should locate by the user manually, not automatically.
Okay, how about is there any additional comments from Mr. Momo? Okay, there is no. Maybe I want to invite Miss Afra, since you are on cam. Do you have any comments about this material today, or do you have any suggestion, especially about your insight regarding the camera course, Miss? Can you join us?
Did you hear me?
I'm so sorry. Can you repeat, Miss?
Did you hear me?
Yes, it's clear.
Okay. Thank you so much. I think it is informative talks. It is the first time I listen about optimization from the Bayesian image. So thank you so much.
Yeah.
Thank you
for
so
your
much.
comments.
Okay, thank you so much, Miss Afra, for
You are
joining.
welcome.
Okay, are still many comments also, Doctor, especially from Mr. Meher Nikar. Really wonderful presentation. I think many participants that appraise and also enjoy this today's lecture, Doctor. And another question from Mr. Arich Noval, Doctor. Can we use patient-centering measurement to educate radiographer for better patient centering? How to approach this for best outcomes?
Yeah, of course. We are, as the medical physicists, we can evaluate our practice, our today's practice. For example, in this example, we can evaluate the position of the patient by using the miscentering parameters. And if we measure the centering parameters, maybe we obtain that the result, the patient have the tendency to be higher, for example, or to be lower. Maybe we evaluate many data, maybe from the 100 patient or 1,000 patient, and we have the data, and then after that we can educate to the radiographer that their practice is not good enough because their setting for locating the patient is so high or so low. So we can educate them to change their practice. So by using this education, we hope that the practice is more suitable. Okay.
Okay, I hope that will answer the question of Mr. Arich. And is there still any comments or suggestion you can share to us with the today's topic? Okay, if no, I think it is time for Dr. Anam to give the closing statement before we end our lectures.
Okay, thank you very much for the joining us until now. By using the IndoQCT, we can measure many parameters directly from the patient, such as the noise, such as the MTF, such as the patient centering, but we have still facing many challenges. Maybe you can ask me, can we measure the NPS directly from the patient? Until now, I have no idea for that. Maybe in the next we will have the idea to measure the NPS directly from the patient images. But until now, we have no idea for that. And can we, for example, measure other parameters directly from the patient? Yeah, I don't know. Yeah, so it is very nice uh, to uh, to do research and to expand our method to be as accurate, very accurate, and also we can measure many parameters beside the already exist parameters. Okay, and inshallah tomorrow we will discuss about the centering with the Professor Wahyu, and we will discuss also about the noise reduction with the various algorithms. Please Please join us tomorrow, and we will discuss many interesting parameters. Okay, see you tomorrow.
Okay, see you tomorrow again. And as mentioned by Mr. Arish in the comment, there are still challenges to measure the detectability index directly from the patient image and also all parameters. If we want to measure directly in patient image is still improving, and hope in the near future we will get the most robust metrics so we can evaluate the patient image clinically directly in the patient image. Okay, I think this is the end of our session. Thank you so much for all participants, and we still have one day left. Tomorrow is the last day of our online summer course, so please stay tuned until the last day, since we will also will discuss the another important topics about the city image quality. And see you tomorrow. Yeah.
Atau Pak Panji aja yang bilang.
Okay. Billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Waalaikumsalam warahmatullahi wabarakatuh.